we going to talk about, because we have 2 assignments left and we have the final project and
Yeah.
presentation,
Yes.
correct?
Yeah.
Are you going to go over those at all, just so we can start?
Yeah, I will give you enough time to prepare your course project and the questions, because we have a Q&A session. Before that, we're gonna finish all homework assignments.
Okay.
And again, if you have any question about your homework, we can still, we can still talk about it.
Okay. I'm just, being swamped and paranoid. That's just what I do. I was just curious. And, thank you, ma'am. I have no idea. Have you got a spare data set?
No, I don't. I can only do like the Q research ones where
Oh.
I just have a free one.
Well, I might have to have you show me how to go in and pull one
Yeah.
of those down.
Yeah, there's actually 3 different websites that you get like free data.
Okay, I might just do that then.
Okay. let me just look at it.
PHEW, right? It's Q.
There's Q, there's another one. Find it.
Yeah, when you came in downstairs, my daughter had just woke up from her nap and wanted to see me. She was calling for me. So
Hey, that's adorable.
she's very much a daddy's little girl.
She's my favorite.
What, most of my kids are daddy's little,
Who's the youngest one? She's the youngest one, though, right?
She's the youngest currently.
So she's a baby. It's a different type of therapy.
Yeah. There's a 7-year gap between her and the next oldest. So
I have a sister gap between me and my sister. I'm the youngest.
Yeah.
my wife still wants another one, but I'm like, I really don't want 6 kids. My oldest is now a teenager.
You still have the stamina and the energy.
Well, that's why I'm wanting to be faculty, is because you can be 90 years old and still making a lucrative income, I hope he brings his laptop today because I'm building his power.
I need to use Zoom.
And I made sure my camera was over far enough so it wasn't
Okay.
blocking yours.
Okay.
I already anticipated it.
Do you need one? We can switch if you need. No, not at all.
Thank you.
How's your
Are you
weekend?
into Randy? No.
Me,
Mhm.
just as usual. Yeah. How was yours?
Busy.
Busy.
Yes.
Do you mind? I'm moving forward to
Go ahead.
the screen to the. Yeah, that's better. Let's see.
All right, I found the website, and you can download it from it in SPSS or like SAS or data.
Free?
Yeah. it's
Wow,
a-
that's
I
awesome.
just like have to log in.
Oh,
Have
okay,
you heard of the ICPSR?
that's good. That's awesome.
All right, so I need to do mine now. Come on, Daniel. There's a better way to focus.
Oh,
Oh my gosh, so
Good enough.
like 3 weeks ago, they were asking me all these questions, which included things like what's your workout song, what's your weight, what's your coach's name, what's your gender, like stuff, some stuff we should probably do.
Right.
And some stuff that
Is
it's
Jenny
important.
here? Jenny?
It's not something.
Oh,
I was like, I have no idea, but anyway, so I followed up and I said, okay, well, what weight do I fighting? Like, it doesn't matter what I weigh, but when do I weigh? Who's my opponent? This was like a week ago, and I should know this at least a month in advance.
Right.
And they replied for like 5 days, and they said the event is canceled. So I no longer have to. It's okay.
Maybe they could the whole event.
Research. Well, they said
Not work.
postpone, but I really think that means cancel.
Yeah.
I don't think they did any advertising. I really don't think they have an opponent. for the meeting.
Right. And those
So
are
I'm
two
gonna
big
look for
ones.
a card,
Okay.
a fight
Yeah,
card
I'm actually
in February or January. So
Yeah,
I'm
the one I
gonna
use for my
organization, you
technology
know,
class is the
has their
ICTSR,
stuff
because when you
together.
download data, it gives you the option to
Really?
manipulate it, SPSS or something else, so like there's different files. that you can edit.
Nice.
Okay, let's get started.
Yeah.
So today we are going to look at model fit. Previously, we did a lot of demonstration about our package. The name is called SEM, and also we learned how to use M+, EQS, and AMOS. Today we're gonna look at model fit evaluation. So suppose we have different models. How are we going to evaluate them? How are we going to tell if that is a good model or not? Okay, so the document, the slides are based on the document listed here, and I have already uploaded the Boland's book, the chapter to ELC, and the session 2, we're gonna do some exercise. Okay, so first, okay, let's try to look at the model. We are going to use the same data set, the older data set, NIOSY 79. So the sample size is 371. We have 3 variables involved. We have mother's education level, ME, home environment, HE, kids, math achievement, math. Okay, 3 columns. So now we assume that mother's education, ME, and the home environment, HE, 2 independent variables are going to predict the kids' math achievement. So this is a dependent variable. This is one of the 2 independent variables. Okay, this is another independent variable. And in this case, we are going to run a multiple regression. So ME, HE together gonna inference math. And that's our data. So it's called R data. It's uploaded to ELC. 3 columns. Okay, ME, HE, math. That's it. Okay. And the first row is a variable names. Okay. So and under this assumption hypothesis, we have the model like this. So together, okay, HE and ME together inference the math achievement. And in this model, we can estimate the variance of HE, ME, covariance between them, the B1, the inference from HE to math, the B2, the inference from ME to math, and the variance of the residual of the dependent variable math. Okay, that is our CAD diagram of the multiple regression model. Now, okay, this is our model to adjust the assumption here. But if I give another assumption, so if the model-based covariance matrix is just our sample-based covariance matrix, what does that mean? So if you look at the sample covariance matrix, we have variance of HE, we have variance of ME, we have variance of the third variable, and we have covariance among them. So totally we have 6 pieces of information. If we assume the model covariance matrix is a sample covariance matrix, that means I do not put any constraint on this model, on this covariance matrix. Then the difference between the S and the capital sigma is 0. There's no residual variance. Okay. In that case, the degrees of freedom is 0. Okay. The degrees are 0. Okay. What does that mean? So we that's it. We don't have any extra information to add some more parameters. And the capital S, the sample covariance matrix, there's 6 pieces of information. We have three variances, 3 covariances. And if the capital sigma equals capital S, then we needed to estimate the 6 pieces of parameters. So there's nothing left. So the parameter, the degrees of freedom are 0. So that model is called, there's a special name for that type of model. It's called a saturated model. Saturated, okay, it's already saturated. There's no more degrees of freedom allow us to estimate the actual parameter. It's saturated. Or you can call it unrestricted because we didn't put any hypothesis on that model. We didn't assume any model if that it's a covariance matrix. So it's also called unrestricted model or saturated model. If you use the path diagram, it can be shown like this. So we have 3 variables, so 3 variances and the covariance among them. Here, we don't have any assumption that ME gonna cause math because for unrestricted model, we don't have any assumption. We don't know if ME actually gonna influence math or not. The same thing here. We don't know if the ME gonna influence math or not. There's no single-headed direction. It's just double-headed correlations. Okay, what's your question?
So since it's double-headed arrow, does that mean that could influence mother's education or home environment? It goes backwards?
It just tells us they are related,
Okay.
they are associated, but we don't know if this is a cause, this is a dependent variable or whatever. This is a cause, this is of course, this is not reasonable, but on the saturated model, we don't know nothing. Yeah.
Okay.
So that's why the causal model, the causal inference model is very important. Last week, I showed you the Nobel Prizes, and 2 of them are kind of like really focused on the causal inference model. So which is the cause, which is the effect?
Okay.
Yeah, if you reverse that, then everything will be totally different.
Okay, sorry.
Yeah, this is also called unrestricted. We didn't put any constraint on this model. But how about the restricted model? The previous one is saturated, unrestricted. If we put some constraint, for example, if we have this single-headed arrow, or if we assume we put some constraint, okay, the B1 is 0. So what does that mean? So HE will not influence math. That is our constraint. Those are some condition, okay, some actual condition on this model. So these are called the restricted model. Yeah, so sometimes we fix some parameters, sometimes we make these two parameters the same. Yeah, so in this case, this means that HE does not predict math achievement above. This is also possible because for models, you can propose many possible models. This is one of them. Although the final estimate, the final model will be proved that this is not a good model, but still it's one model. You can just do the test. So this is one of the restricted models. Yeah, so for example, in this model, because we don't need to estimate that this parameter, B1 is not necessary. So we only have 5 parameters. But as we discussed before, we have 6 pieces of information. Now we have 5 parameters. We have 1 degrees freedom left. The degrees freedom is 1 in this case. Okay, so this is not saturated model. For saturated models, the degrees freedom is always 0. Okay, 0. But here in this case, we have 1 degree of freedom. And of course, that is one of the restricted models.
And of course, by restricting B1 to B0, so if we put the constraint on B1 to fix at 0, then the difference between the capital S and the capital sigma is not 0 anymore. There will be some difference. Yeah, and if the difference is much larger than 0, then that means what? That means it's not a good idea to put that assumption, to assume that B1 is 0, because the model-based covariance matrix and the sample covariance matrix has very big difference. That means, okay, the model is not reasonable, it's not good to explain the data here. You have to make sure your model and the sample are really close to each other. So you can use that model to explain the current data, so that you can tell your story, okay, why that, what happened. But if your model and your data really have really big difference, then you cannot tell your story perfectly. Okay, so in other words, B1 equals 1 is not a good model, but this is based on, okay, the difference between the S and the capital sigma. So we have another kind of like a concept called nested models. Previously we said unrestricted model, restricted model. Now let's move forward to nested models. What are nested models? If a model can be derived from another model by imposing some linear or nonlinear constraints, the resulting model is said to be nested in the other model. So what does that mean? Suppose we have two models. One model can be derived from another model. So you can think that, okay, this model is kind of like a model constrained or nested within the other big model. So after we put some constraint, we have another new model. So these two models are nested with each other. You can think about, you can treat it as like a simpler model or more complicated model or small model, big model. Some people talk about that. Okay. But anyway, these are nested models. Yeah, also some people call them hierarchical models. So a restricted model is nested within an unrestricted model. Restricted model, think about that. We put some constraint, and then we have restricted model. For unrestricted model, it's kind of like a fully flexible. So restricted model is nested within the unrestricted model. The unrestricted model is kind of like a larger model. It's more broad. And then the restricted model becomes smaller because there's some constraint. So this is kind of like a small model, and we have another larger model. So these are nested with each other. Yeah, so all the models we showed last class, actually we have the our regression code, we have different models are nested within the unrestricted model or the saturated model. And then remember that we did the R, M plus or EQS or AMERS do the data analysis. So when you look at the output, there's a one part of the output called the model fit information. It provided the information on model chi-square, degrees freedom, or p-value, AIC, PIC, something like that. If you remember the output of M plus or R. So what does this part? Okay, what is meaning? What does this meaning? So we're gonna look at model fit and model comparison. Can you see it? Because this is because of the sunshine here. Is this better? Yeah. So for any restricted model, the S and the capital sigma are not the same. Okay. So the difference between them is not 0 anymore. Okay, but how big is that difference? Okay, we're gonna quantify that difference. So basically we have a test. It's called a chi-square test, or some people call it a chi-square difference test, to quantify the difference between two models. And this test is only for nested model. We just explained the nested model. For those type of models, we can use a chi-square difference test to compare those two models. There are some other models are not nested with each other. Then in that case, we're gonna use some other tests. Okay, for nested model, we are going to use chi-square difference test. But what is chi-square test? Okay. Let's start from the likelihood ratio test. Likelihood ratio, okay, likelihood ratio, it's a ratio. It's a ratio. Ratio of what? Likelihood. So the top part is the bottom part is likelihood, okay? And we assume that there's a gamma, which is a ratio. Okay, this is a up limit, okay, supreme up limit of the likelihood value of the theta based on the current data X. The solution range is theta 0. What is theta 0? Theta 0 is a subset of the whole solution space, okay, theta, which is theta. And then our MLE, the maximum likelihood estimation method, is element of this space, okay, this space. So this is a restricted area. This is a restricted solution space. This is an unrestricted solution space. So this space is smaller than this space. So, but anyway, we're gonna calculate that likelihood based on theta 0 and the theta, and calculate the ratio. The ratio, suppose it's called lambda. What is likelihood ratio test, or LRT? LRT is any kind of test that has a restriction region of the form of this lambda, less than some value. The C is constant here. C is between 0 and 1, some value, okay. Any kind of like this test is called a likelihood ratio test because it's a ratio of between two likelihood, and we compared with some constant. It's a test. So suppose this one is MLE. MLE is maximum likelihood estimator based on the subspace, restricted space, theta 0. And the theta hat without 0 is MLE, is the maximum likelihood estimates of the unrestricted area, the capital sigma here. And then the likelihood ratio test becomes a lambda here, okay, based on this likelihood and this likelihood, because by taking the MLE, theta 0 or theta, it has already reached the maximum number, superior number. So it's the same, okay? So this ratio is always less than 1 because this space is smaller than the larger space. So the solution is always within the larger space.
So as the closer it gets to 0, the more
Yeah.
likely you can tell inference on
Oh,
if it's
no,
nested or
that's
not.
sorry. Yeah. So we have another, yeah.
Okay.
So based on that lambda, we take a log function and then we times 2.
Okay.
This statistic has really good property. Why? Because it has been proven. It has been proven that it goes to chi-square distribution. If we have single parameter, if the theta is the scalar is not a vector, then that is a chi-square with one degree freedom. Asymptotically, what is asymptotically? So that means when the sample size goes to positive infinity, it goes to chi-square. If the sample size is so limited, it's close to chi-square, but it's not exactly like the chi-square. It's asymptotic, okay? It's not exactly the same thing. But when the sample size goes to larger and larger, it's very close to that distribution. So here, let's look at the lambda. Lambda is a ratio, okay? Lambda is a ratio which has shown in this slide. Likelihood based on theta 0 over the likelihood based on the theta. Now, if you take a log, because we have to take a log function lambda, log of a ratio. Think about the rules of logarithm. log of a ratio is log of the top part minus the log of the bottom part. In the review session, in the first session, we have this property, okay? If you cover -2, the log of the ratio is a log of the top part minus the log of the bottom part. And of course, we need to times -2. This is called the chi-square value of a model. Okay? Yeah. And for the multi-dimensional case, if the theta has many parameters, then again, this statistic really is very good. It asymptotically goes to chi-square degrees freedom, chi-square distribution with a degrees freedom of m. M is a dimension of the theta. Okay, so it is still good for multivariate case. Because of the good property, then we're gonna focus on this part. You can just focus on this, okay, log likelihood function, okay, times 2. This is called chi-square value. And then you have another part, -2 times the log likelihood of the full model, okay, the unrestricted model. So people called this one, okay, it's deviance score. What is a deviance score? Is a -2 of the log likelihood of the reduced model. Reduced model actually we shown as theta 0. It's a smaller model. It's the previous term. It's here. Okay. This is a reduced model. Okay. This is a constrained model. This is a restricted model. Restricted model. Log likelihood of the reduced model minus the log likelihood of the full model or the unrestricted model. Then times 2. If you just do further calculation, next 2 times the first term here, and minus the -2 times the second term here. And this term is called a deviance score. Some people use a delta chi-square. Delta chi-square, so that means chi-square difference. Because this is a chi-square, the chi-square of different models. The difference score between these two chi-square values. So that's why it's different, delta chi-square. Or some people also use g-square to show it, okay, to show that value. That's one part we needed to obtain for chi-square difference test. That's one step. There's another step. You also needed to get the change of the degrees freedom. That's why we said degrees freedom a lot, because you need to calculate the change of the degrees freedom between two models. Okay, the number of, and also think about the degrees freedom is number of information minus the number of parameters. So the difference in the degrees freedom is the number of information is the same for both models, minus the number of parameters. So if you do the subtraction, okay, cancel the number of information, we have the number of parameters for the full model minus the number of parameters for the reduced model. So number of parameters for full model is always larger than the number of parameters for the restricted model. Because it's restricted model, okay, we have some constraint. So the number of parameters for the smaller model is smaller than the number of the full model. So this value is always larger than 0, okay? So we have these two different scores. Based on that, we can do the chi-square difference test. Yeah, I just copied the previous 2 different scores on top of these slides. The chi-square difference score, it's -2 log likelihood of the reduced model minus the -2 times the log likelihood value of the full model. And the change in the degrees freedom is number of parameters of the full model minus the number of parameters in the reduced model. Okay. Yeah, this part is It's really, I don't know if you can see. It's almost blank. Yeah, yeah, I'm sorry.
We could
Is there
switch
any
to
better
the,
way to cover this part?
no, but next class we could go to that end of the class.
Oh, yeah, you're right.
Because
Yeah.
the
we
sun's
can-
not there,
Yeah, yeah. Yeah, I'm sorry.
or part two.
So for MAE, the larger the log likelihood statistics, for example, the LL value, okay, the better fit. Because we try to maximize the likelihood, it's called the maximum likelihood estimation, the maximum likelihood. We're trying to maximize that. But if we take a log, okay, the log, look at the log function. This is 0, this is 0, this is 1, this is x, this is the likelihood value here. Okay, if the take your log, this is a log function, then all the values are negative because the likelihood is between 0 and 1. If you take a log, the value, because x is between 0 and 1, so all the log values are negative, less than 0. So these are log values, okay? And the likelihood, we try to make it as large as possible, so close to 1. So if it's close to 1, then the log still is negative, and yeah, maybe it should be close to 1. Okay. And then we times -2 to make it a positive. Okay. So we use chi-square value instead of the log value. So basically, what is the logic of the chi-square difference test? We're trying to compare the two models by using their chi-square values. Okay, so we want to know if the reduced model is significantly worse than the full model or not. Okay, so this is our goal to run the chi-square difference test. Because the difference, the deviance score and deviance statistics quantifies the difference between these two models. So we want to compare with a chi-square distribution. That's why it's called a chi-square test. Okay. We want to compare the deviance score with a chi-square distribution to see if it's significant or what? Significantly worse than the full model or not. That is a full sentence. If it's significant, if the difference is significant, that means the reduced model or the constrained model is significantly worse than the full model. If it's significant, we should discard as a restricted model because that is too bad. Okay, it's significantly worse. We should keep the full model.
When you say full model, you mean the unrestricted?
Unrestricted model, yes,
Unrestricted,
correct.
okay.
Yeah, so we
We
have
switch
smaller model.
terms and
Yeah,
that's following.
we have the smaller model, we have the middle model. This is a restricted model. This is a
Okay.
full model or unrestricted model. Yeah.
Sorry, I just didn't catch the shift in
But
terms.
sometimes both are restricted model.
Correct.
But still they are nested with each other. So you cannot say that the other model is unrestricted. Sometimes both are restricted, but we still needed to compare these two models. Okay.
Thank you, ma'am.
So I cannot see the words here. Yeah, I needed to look at my slide. I'm sorry. No. So given the same degrees of freedom, the same difference in the degrees of freedom, the larger deviance, the worse the reduced model. Yeah, think about the chi-square distribution. If we fix the degrees of freedom, the larger the difference, the larger the value, the deviance score, the worse the reduced model. Okay. And then the distribution should take the degrees of freedom of the delta degrees of freedom. Okay. The distribution of the chi-square distribution is taking the delta df as the other distribution. So that's a basic logic of the chi-square difference test. It's based on the chi-square distribution here. Okay, it's based on this chi-square asymptotic chi-square distribution, and then we compare the difference score between two models with the chi-square value to see if the difference is significant or not. And in SEM, the evaluation model based on chi-square difference test. Okay, so we have F value. Remember that we have FML. So it's a log, the determinant of the capital chi-square and minus the log of the determinant of the S. And also we have some trace part. Okay, and we also have the minus the P. Okay, the degrees freedom of the X and Y, not the degree freedom, sorry, the dimension of the X and Y. So that F value times N minus 1, N is the sample size minus 1 times the FML is the chi-square here. So you can prove that. Okay. So that means you can just look at the F value. And the degrees freedom here, we calculated this degrees freedom previously. We have number of parameters P. Okay, P is the number of variables. I'm sorry, not the parameters. P is number of variables in the original data. P times P plus 1 divided by 2. That is the number of information. And minus Q. Q is the number of parameters. Okay, the difference between these two is the degrees freedom. And the C value, N minus 1 times F follows the chi-square distribution. Of course, it's asymptotic. Okay. And actually, the Boland's model, Boland's book also provide the proof of this part. It shows, okay, so from here, this part is natural from here to here. They give us the derivation from this part to this part. And this part is based on maximum, based on the likelihood function of the normal distribution, okay? Yeah. So for the chi-square value, okay, so we can call the C value. C value is a model chi-square. A big value indicates a bad model. Okay. So it's not good model. The smaller the better for the chi-square value. So let's look at this formula again. First, we try to get the deviance score between two models. Okay, what is the deviance score? It's just difference between two models chi-square value. Okay, the chi-square value of the reduced model minus the chi-square value of the full model. That is the first step. The second step, get the difference between number of parameters between the two models. Okay, number of parameters for the full model minus a number of parameters for the reduced model. And then when these two parts are ready, we're gonna compare that value with a chi-square distribution. Chi-square distribution with what? With which degrees freedom? That is a degrees freedom. Okay, this is the chi-square value compared with a chi-square table or chi-square value with that specific degrees freedom, and to see if it's significant or not. We will have the exercise, or we will have lab next time, next session. So far, I just introduced the abstract part. We don't have any exercise, but when we have the lab, we have the actual model. We can just calculate all of these chi-square values and do the calculation. Yeah. So that's chi-square.
So if you choose one of the models that's nested,
yeah,
do you typically show this calculation and you justify why you chose either the unrestricted or the restricted model?
That based on your choice. You have some reason to choose some models. You believe that some models should explain your data well, but you don't know which one is the best among these two. In that case, you're gonna run the chi-square difference test. to see, okay, I'm gonna pick A or B. That is the reason. That tells you which one you're gonna keep, you're gonna discard. Yeah,
But like part of a dissertation or publication, would you justify saying,
yeah,
I
you can do that.
chose this because of this?
Yeah.
Okay,
You can say that, okay, we have some candidate models available.
okay,
And that model explain that part, this model explain this part. You think both are all good. And then you run the chi-square difference test. And finally, your conclusions that say you're gonna keep A. Why? You have some reasons here. Yeah, you have
Okay.
some support here.
I just tie in functionality to what,
Yeah, this just tell you,
which one's better.
yes,
Okay,
if they are nested. If they are not nested, we're gonna use some other modified indexes. If they
Yeah.
are nested,
The
we use
goodness
a
of it.
chi-square difference test. Yeah,
okay, thank you, ma'am.
yeah, thank you.
Oh, what goodness of it.
Oh, yeah, and then when we look at the M plus output or output, we have some other modified indexes. For example, GFI, AGFI, what are these, okay? GFI is short for goodness of fit index, okay? Goodness, G, fit index, goodness of fit index, GFI. AGFI is short for adjusted goodness of fit index. Okay, so these are two indexes. What's the definition? GFI is defined by this formula. Okay, 1 minus F over F0. So what is F? What is F0? Okay. F is a function value for the current model. So you have F, so suppose you have FML, then you have the formula. Yeah, log the determinant of the capital sigma and also trace something. Okay, that F for the current model. And F0 is for the model when the capital sigma is 0. This is a 0 model, okay, it's a null model. So the null model actually tell us, okay, there's a no relationship among these variables, okay, and we have some. This is a really not good model. So you're gonna compare the current model with F0, and then 1 minus that value, okay. So we also have the detailed explanation for the GFI. So if you go to the Poland's book here. Here, okay. So the F, this can be simplified by this term. So GFI goodness of fit and AGFI adjusted the GFI. And the top part has been simplified by, okay, the trace of the inverse of the multiple covariance matrix times the S and the minus the identity matrix, and then square and got the trace, okay. The bottom part, we have this term, okay, we have this part. And for the AGFI adjusted, how adjusted this GFI? So it's the same thing, 1 minus, okay, this is F and F0 part, and here we have the Q involved and the degree freedom involved. Q is number of parameters, okay, so we have Q times Q plus 1 divided by 2 degree freedom, and then this GFI is based on this GFI. Okay. What is Q here? Sometimes the Q in the textbook means the number of information. Let me see. Q, you need to check what's the meaning of Q here. And so that, yeah, here we have Q is number of parameter. Okay. Oh, number of dimension number, okay, of the model.
It's not the same as our notation here. That is for the maximum likelihood version. So F, we have different version. We can have F, ML, F based on the weighted least square, or F based on the iterative, okay, least square. So we have other set of versions of the GFI and the AGFI. Okay, let's see the other version. 7.60 is for the ML, for the maximum likelihood version. But for the weighted unweighted least square, okay, then we have the GFI defined by this formula. Okay, so here this is the trace of the sample basic covariance matrix minus a model basic covariance matrix squared, and then got the trace, and also the bottom part is the trace of the sample covariance matrix. Because in that case, the model basic covariance matrix is 0. In the F0 case, now model, we assume that this one is 0, so we don't have any model basic covariance matrix here. And adjusted GFI is the same formula, but the GFI should based on this definition. Okay. And also we have another version of this square, GLS. Then the GFI is defined by this formula, and the HFI is defined by this formula. So you can see that based on different F, different description function, you have different version of the GFI. Okay. And that is a HFI. It's a modified version of GFI. So if the D0 here is a P times P plus 1 divided by 2, then the P is Q here. This is the P. In the textbook, in the bonus textbook, the Q here is P in our slides. Okay, so we use different notations. The Q is a P in our slides, a number of variables in our model. But in our slides, the Q means that the number of parameters is different. Okay, so it's different. And also, yeah, for different version of the description function, we have the different version of the AGFI. That is the explanation of these two indexes. We also have NFI and NNFI. So what are these? NFI is short for normed fit index. Okay. NNFI is short for non-normed fit index. And we also have the formulas listed here. So NFI is defined by 1 minus F over FB. Again, so it's a ratio, 1 minus a ratio. So what is F? What is FB here? FB is for the independent model, okay, or the baseline model, or the non-model. I will explain what is a baseline model, what is the independent model, okay, or non-model in the next session. And F is just the current model, the F value for the current model. But which F? Again, it depends on your estimation method. It's ML or LS, so which LS? It's ULS or GLS. We have different versions. So for NFI, if a value is between 0.9 and 0.95, that means the model is acceptable, okay? And if a value is above 0.95, that means, okay, it's quite a good model. So you're gonna check the NFI value. And NFI is not known. Okay, so we have F based on the baseline model divided by the D based on the baseline model, and F for the current model divided by the D, degrees freedom for the current model, and also F based on the baseline model divided by the D for the baseline model minus 1 and minus this part. Okay, reciprocal of N minus 1. Okay. So we have the model penalty term. If we compare the NFI, okay, if we compare these two parts, we have the model penalty term. We have sample size involved. We also have the degrees freedom involved of both models. And how to interpret the NFI? So we should compare it with 0.9 and 0.95. Yeah, NFI is also called the Bentonov or net fit index. And NFI is also called the Tuckler-Lewis index. Okay. So let's look at the baseline model. So here we talk about the B. What is a baseline model? Okay, baseline model or non-model, independent model. We assume that all of these variables are independent. There's no association among them. In other words, that's our model. Okay, so just variance of 3 variables, no covariance among them. All the covariance are zeros. So if you have the covariance matrix, it's just diagonal. It's diagonal matrix, no covariance, no off diagonal elements, because we assume that these are 0. That is called the baseline model. No relationship among all observed variables.
So since it's also called the null model, would this be assigned to our null hypothesis saying?
Oh, it's different. Oh, it's different.
Okay.
Null hypothesis and null models are totally different things. Yeah.
All right.
So for M plus, they also provided the chi-square value for the null model, okay, or the baseline model. But this model, we can see that it's a very bad model because all variables are assumed to be independent. This is a really, really bad model. Okay? It's not a good model. But in order to get the NFI and the NFI, you have to use some information are based on this model, and you do the comparison. Okay. If the baseline model is introduced here, actually the F value is quite large, and the ratio of Fn over Fp is very small. Okay. And then 1 minus small number is close to 1. So the closer to 1 means it's the better. But if the current model is close to the baseline model, then that ratio is close to 1. This ratio is close to 1, then the whole NFI is close to 0. So that means that's a bad model. That means that the current model is very close to the independent model. Independent model is a not good model. It's bad model. So closer to 1, the better the current model. Okay, so that's for the pair of NFI and NFI. Actually, the same logic here. This is the F0 is not baseline model. The F0 is 0 model here. It's even worse. So if the F is close, it's also the bad model. Okay. So if the F is very close to the F0, it's a bad model, then the ratio will be close to 1. Then the difference between 1 and that ratio is close to 0. So GFI is very close to 0, bad model, because that's close to the 0 model. So we should make that value large as possible. Okay, just away from the bad model. F0 is not good. And same for the AGFI. Okay, closer to 1, the better model. For these two sets, okay, the closest one, the better model. But if it's close to 0, it's not close to 0, if it's less than
for example, 0.8, you can say that, okay, that's not a reasonable good model. That's not a good model. You can just discard that. Okay, now let's look at another model fit index called the CFI. Okay, CFI is for comparative fit index. The formula is provided here. The format is quite similar to the previous sets. Okay, it's 1 minus some ratio. Okay, for CFI is 1 minus the maximum value between these two parts, the chi-square value minus the degree freedom and 0. So that means we want to make sure it's a positive. Okay. The bottom part is the maximum between these two values, chi-square of the baseline model and the degree freedom of the baseline model. And take the maximum between that value and 0. So we want to make it positive. Now, chi-square B is the chi-square statistics for the baseline model. Degrees freedom D is the degrees freedom for the baseline model. And the chi-square is the chi-square value for the current model. For the model is being is tested. Okay. And the degrees freedom is the degrees freedom for the current model, the test model. And because chi-square values can be also shown as the expression of n-1 times f value, you can use this f. Okay. And the chi-square for the baseline model is n-1 times the f description function of the baseline model. Okay. These two versions are the same. So then for CFI, if that value close to 1, that means a good model. Okay. Closer to 1, the bad model. And usually we say that if a model is fit, okay, then the value should be larger than 0.9. If the model have the CFI value less than 0.9, for example, 0.85, then it's not good model. You can just think about that, propose another new model. And the logic is the same. We're just trying to compare with the current model with the baseline model. Okay. The closer to 1, if the ratio between two maximum values is closer to 1, it means a bad model. Okay, because it's very close to the baseline model. Okay. And then the CFI is close to 0. So that's a good, it's not a good sign, not a good model. Any questions so far? Any question? Okay, then let's look at another index called RMSEA. Okay, it's really, really important, RMSEA. It's short for root mean square error of approximation. Okay. And the definition is here. RMSEA equals the square root because it's root. Okay. Root, square root, and maximum between these two values, which make it try to make it positive. Because sometimes this term will be negative, then you cannot take a square root of the negative number. So by using that, you make it positive. And here, this part is the chi-square divided by the degree freedom, and then -1 divided by n-1. With the chi-square value, you just observe the chi-square test statistics for the current model, for the model being tested. Degrees freedom, just degrees freedom. The df is a degrees freedom for the model. And n is the sample size. And if you use another version of the chi-square, okay, it's n- times f, then it becomes this part, okay. because of this equals a minus 1 times f, so we cancel the a minus 1 here, so it becomes a degrees freedom. F divided by the degrees freedom, and also minus the right side part here. So for RMSEA, the criteria is different. You are not going to compare with 1. Instead, you should compare with 0. Closer to 0 is a better model. Okay, so if the RMSEA value is less than 0.05, indicated a close fit of the model. If that value is less than 0.08, indicated that it's a reasonable good model, a reasonable model. If it's larger than 0.1, means okay, it's not a good model, it's a bad model. Okay, so that's for RMSEA. So all the model fit, all the software will definitely report RMSEA. But some software will report NFI and FI, some will report GFI, GFI, some report CFI. But always they will report RMSEA. Okay, this index is all will be always there. We have another version of the mean square, so it's called the standardized mean square residual. Okay, so SRMR. It's a standardized difference between the observed covariance and the predicted covariance matrix. Okay. And quite same as the RMSEA, the value should be compared with 0. Okay. A value of 0 indicates the perfect fit. Okay. There are some limitations. This measure tends to be smaller as sample size increase and as the number of parameters in the model increases. Okay. So a value less than 0.8 is considered a good model, a good fit. 0.08, I'm sorry, not 0.8, 0.08. All of these are 0.05, 0.08. Okay. If it's larger than 0.8, then it's probably that's a very bad model. Okay, so that's for SRMR. In addition to those, SRMR, MSEA, CFI, NFI, NFI, GFI, GFI. We have AIC, DIC, SSDIC, ADIC, a lot of IC, and also we have DIC, operation case. These are one family of the information criteria, okay, IC series. So we mentioned the BIC. Remember that we calculated the BIC and the EIC in last class. We have the chi-square value, we have the sample size, we have number of parameters. We manually calculate the AIC, BIC value. So formally, now let's need the definition of AIC and the BIC. Okay, that is a formula to define BIC. BIC is -2 times the log of the likelihood value plus the Q. Q is number of parameters, okay, number of parameters in that model, and the times log of the sample size, and here is the sample size. We also have AIC. AIC is defined as quite similar. Let's look at the form. Okay, the first part is exactly the same. The second part is 2 times Q. Okay. In this case, the sample size does not involve, but people found that, okay, maybe the sample size is gonna influence the model fit. So they also consider the sample size. So they put the log n here into the consideration. So both of these parts are called the penalty term. The first term is called the model fit part. Okay. And we have some other version of IC. Okay. For all of these values, the smaller the better. If you want to compare two different models by using EIC, BIC, the smaller the better. They choose a smaller value. Choose a model with a smaller EIC or BIC. Okay, so I just introduced the actually that's not all. Okay, some just part of the model fit indexes. If you're interested in this part, you can also read this chapter. So we have some detailed explanation for the model fit evaluation. Evaluate the model. Overall model fit measures. Yeah, if you want to know more about the chi-square test or other indexes, you can just read this chapter. Okay. Okay, question? Question for the question for the beginning, for the first set, the first part of today's talk. Next session, we are going to have a lab, so we use it. Actually, we can use either of these software and to do the model comparison or model evaluation. But we're gonna focus on R. Of course, you can use UPS, you can use M+, you can use other software. But just use the RSEM, the regression code. I have already sent the code 2 weeks ago. Okay, so you can just use that code to run the comparison, model comparison, the model evaluation.
The code for which one?
For the regression part, I repeated send the code for today's class. Yeah,
Okay.
it's the same code, our code. So last class we just mentioned that we can run different models, but we didn't do any comparison. We don't know how to compare them. So next lab we're gonna, yeah, we can just try to pick some of them to look at the chi-square value or the ASPIC or other values. Any question? Any question? And then we can have a break. Okay, we can have a 15 minutes break. And let's come back. Let's continue session 2 at 7:05. Thank you. Restrict this model to get this model. Okay, so this is a kind of like a smaller model. This is a full model. This model is nested within the full model. The restricted model is nested within the full model. So the degrees freedom, so let's, in this case, the number of parameters in this case, it's 6. We have 1, 2, 3, 4, 5, 6, 6. But here, because we put a constraint here, we only have 5 parameters. We don't need to estimate these 2 because these 2 are assumed the same. So the degrees freedom, the number of parameters of the full model is larger than the number of parameters of the restricted model. The difference between these 2, the degrees freedom, the difference among the degrees freedom is 1. Okay. And the next model, remember that for next model, if you want to do the comparison, you can use a chi-square difference test. The next problem is trying to get the chi-square value of these 2 models. The chi-square value of this model, the chi-square value of this model. Oh, I haven't started. I'm sorry. Yeah. Okay. Yeah. Okay. So I just introduced these 2 models. So by putting the constraint of B2 equals B1, this model is nested within the former model. And now next task is to compare these 2 models. Which one is good? Which one should we keep? In order to use a chi-square difference test, we have to get the chi-square value of this model, chi-square value of this model, get the difference. Get the difference. And also we're gonna check the difference between the degrees freedom of the degrees freedom between these 2 models. And we have the formula. The change of the degrees freedom also equals the difference between the number of parameters. We have already obtained the number of parameters. The difference is 1. Okay, here we have 6. Here we have 5. So the difference is 1. But how about the chi-square value? We have to run the model. We have to run both models and to get those values. Okay, so how to run those 2 models? Let's have a review because actually we have already done this part and I think it's 2 weeks ago. So let's have a review. The first step, we're gonna install a SEM package or install package. If you have already done that part, you don't need to do the second time, but you need to use a library to attach that package to make it ready for us to use. And then you can also set your working directly to your current model, to I'm sorry, not the current model, current folder, I'm sorry, to the folder where you save your data file and your R code. Okay, so it should be your own folder, your own directory. And then reading your data. So the data is called rdata.txt. Okay, so read the data. If you haven't set your working directly, you have to include all of this text, the really long text. But if you have already done this part, if you have already set your working directly, you don't need to include all of this long text. You can just directly say, read the table of the rdata.txt. And of course, you're gonna include in the header part, the table header. And the file is called NLSY saved in your current R working directly. You can check the data part. Okay, the head is the beginning part of your data set and row. Okay, how many rows, sample size of this data set. That's your data part. Okay, make your data ready. Second step, we can also calculate the covariance matrix. By using COV, you calculate the sample-based covariance matrix. Okay, COV of the data set. Automatically, you got S. That is the second step. And then we have third step. You need to specify a model. This is our test diagram. So you can translate. You're gonna translate the test diagram into the R script, R code. So we use a specified model that is a function inside the package SEM, and then we specify each parameters from here to here. We just tell R, so which parameters we are going to estimate. So HE to math, we call it B1, and the ME to math, we call it B2. Variance of HE, variance of ME, covariance between these two, and the variance of the residual of the math part as 3. Okay. All of these 6 parameters has been specified in the specified model function. Okay, inside of this function, you specify these lines. You have to use a pound sign to finish all of this code. You have to use this sign. Otherwise, are just keeping you. Well, what is your next command? What is your next line? So you have to use sign to end it. Third step, ready. Okay, now we have the final step, run SEM. SEM is another function inside of that package. We have your model ready. Yeah, this is your model. And this is as we obtained in the previous slide, sample coherence matrix, sample size here, and run. Okay, this is a review part. I'm sure that everyone has already learned these 4 steps. Okay, so let's go to R Studio. Yeah. Oh, question? Yeah.
I have a question. So for the homework,
Yeah.
we can choose which package software we want to run the analysis through.
Which package you are going to use?
In place.
That's also, yeah, it's doable.
Okay.
Yeah. But why do you want to choose M+? You have M+ or installed in your computer?
I do when I understand it better. Who they
Oh,
are.
okay. Okay, that's good. Yeah. Yeah, because R is free, so I always recommend R. But
Right.
if you want to use M+, it's good. Yeah.
Thank
Okay.
you.
But actually, I'm gonna show you a lot of code of R. So for the homework, you will have homework 4.
Mhm.
Homework 4, you only need to modify a little bit for the current code I provided. If you want to M+, you're gonna try to write the code by yourself. Yeah, okay, is that okay? Yeah. But of course, you can also modify my code. It's quite similar. Okay, please open R Studio. R Studio here. And yeah, we have, yeah, and suppose you have opened the file and choose a file, R file called the regression underline SEM.R. So this is old R script. Old R script. We use it when we learned R. So when it's ready, yeah, so you can try to run the library part. Okay. Yeah, you don't need to install package because you have already finished the package part earlier. So highlight library and make it ready. Please skip the middle part because in that code, I have 2 parts, simple linear regression, multiple linear regression. For simple linear regression, we can skip for today's lab. Okay, that is an exercise for the previous course. So please go ahead, continue to scroll down, and then we have the multiple regression example. So we're gonna use a multiple regression example. Please set your working directly. Okay, so this should be your own folder. So here I just give you an example. You can manually set the working directory by using the code here, or please go to session in the menu bar, click session, and click set working directly. And the third option, choose directly. And then you're gonna choose your own folder. Okay, so go to your own folder. So suppose, yeah, so it's my folder. So I have already done this step. And in that folder, you have already downloaded the data. You downloaded the data from VLC, save your data to the folder, okay. And then read the table, okay. By using read table to import the R data text file to R, and you call it NLSY. So NLSY is ready for you. Of course, you can verify the information of the data set by running head, the beginning part of the data set. That is our data set. And you can also check the sample size by running n row 371 individuals. That's our first step. Okay. Second step, actually, yeah, I put the second step after the task diagram, but it's okay. Okay. So you can go to the line of 69 or 70. Run the sample coherence matrix. In the slides, I said this is your second step, but actually second step, third step of second step and third step can be switched. Okay. So suppose you want to calculate S. So highlight this part, run S, and you can check S here. In the console panel, you can check the S. That's it. This is the covariance matrix of these three variables. Variance of ME here, variance of HE here, variance of math here, and covariance among two of these three variables. 6 pieces of information. And then let's go back to the task diagram. This is your third step. Okay, so we can highlight all of these by including the pound sign. This has to be run at one time. Yeah, for sure.
Okay. Well, I think yours is so. Oh, never mind.
Okay.
Well, my question was gonna be the covariance. So the last
Covariance here. Yeah.
test you did was covariance between
Yeah.
Each variable, right?
Yes.
Okay.
This is a covariance between ME and HE.
Okay.
This is a covariance between ME and math. This is a covariance between HE and math.
Right.
3 covariances and 3 variances.
Okay.
In together, we have 6 pieces of information
Right.
ready for us to use. So that's why we can at most estimate 6 parameters. We cannot estimate 7 parameters. That's not allowed
Right.
because we only have 3 parameters. P equals 3.
Right.
3 times 4, P plus 1 divided by 2 is 6.
Right.
That is the maximum number of information. Yeah. So highlight, choose the model part, including the pound sign, and then click run. Okay. So we have 6 records, 3. That's a third step. And then finally, we can run SEM. Okay, this is the fourth step. Suppose the results are saved to, okay, this is the name of the object at model 2, multiple regression. That's my name. So you can also change it to other name. So this is my model, multiple regression here, which is defined here. And then the S is calculated here. All of these are ready. The sample size is 371. So highlight this part and run. That's the output. Okay, so it's really simple. You can also use summary and ANOVA functions to see the details of this result. So we have B1 estimated here, B2 estimated here, S2, S1, S3, covariance between ME and HE. That's it. It's really simple. Let's try summary and ANOVA. Summary, yeah, just try highlight the summary of the result. This is our result, run. That's it. We have a really long table. So if your space is not long enough, see, it just use 2 parts of the table. So they just, so we can just, we can make this space large enough to show the whole complete table. You don't need it to separate them. Okay, that's good. Okay, so we have parameter estimate, B1, B2, S1, S2, S3, S1, 2. Estimate standard error, z-value, probability, and that is explanation of B1. Okay, B1 is MHE equals math. B2 is ME equals to math. Okay, let's scroll up to the beginning part of the summary. Here we have model chi-square value. you're gonna write down this value if you want to use a chi-square difference test, because this is a chi-square value for the current model. Okay, and of course, for the current model, degrees of freedom is 0 because we have 6 parameters. 6 minus 6 is 0. And AIC, BIC are provided here. And that's it. Okay, so we have normalized residual, we have R square for the dependent variable. That's it. It looks very simple. Where are those model fit indexes? Now, let me tell you a trick. If you want to see all the model fit indexes, you have to make this option open. So in addition to summary, you have to add this option, okay, fit indexes, and just add all the possible indexes here. Okay, so just run the second part of the summary. Highlight the summary. Here, we're trying to ask R to show, to report the GFI, RMSEA, NFI, NFI, CFI, RNI, IFI, SR, MR, EIC, EICC, BIC, CIC. Okay, almost all the model fit indexes. Okay, try to run this part. Now, let's look at the model fit. Still not all of them, because some of them are not reported, because if the degrees freedom is 0, it cannot do a lot of like calculations. So you can see that some are missing. Not all of these are reported here. But you have goodness of fit. You have GFI here. AIC, in addition to AIC, BIC, you also have AICC and the CAIC. These are verified, important, updated version. Okay, the revised version of AIC value. But the other values are missing. It's okay because this model is.
Now, you said the goodness of fit, the closer to 1, it's a bad fit, correct? Because you want 0.08?
It's a good fit.
It's a good fit.
Yeah.
If it's close to 1.
Yeah,
Okay.
it's good fit. Yeah. So that's okay because the degrees of freedom is 0. But anyway, it just provides you more information than the previous result. Okay, that's for the current model. Then let's look at the model 2. Okay, model 2. I think we should. Which model should we? Okay, so let's go back to slides. Let me make sure the model 2. Everybody understand the model 2. This is a result for the current model. Okay, and I just copied the result here. Now let's look at the model 2 here. This model by constraint B1 and B2 have the same value. How to run the second model? Here, that's a model, that's a code. For the third step, specify model, we're gonna make sure these two are the same. In R, we put the same name, okay? We put the same name. In the previous code, we use B1 and B2, but here we use the same name, B1. In M+, if you're trying to use M+, do you remember how to put this constraint?
Put a number there.
Yeah, so you need to modify your code if you want to use M+ for your homework 2, homework 4. So you're gonna change your code a little bit by putting the same number, parentheses, okay, under the after the
In homework 3, you should use 2
coefficient.
in the bottom
Yes.
part.
Right, to put them both the same.
Okay, so this is our code. We assume these two paths have the same value and run SEM, okay? So let's go to R again.
I have a
Let's go.
question.
Yeah, question,
Okay.
yeah.
So, no, me jumping ahead for the homework, we initially run the baseline model, right?
No. I will explain homework
Okay.
4. Yeah, after we talk about the lab. Yeah.
Okay, thank you.
Yeah, okay, thank you. Yeah. You don't need to know the baseline model. It's nothing related to baseline model. Yeah.
Okay.
Okay, so go to R Studio. And then find the correct code for the second model. Let's see. I provide you a lot of models, so which one is the,
It's at 141.
okay, 141, good, okay, here, that's it, yeah, for model 4, actually, I provide you a lot of alternative models, so this is a model to correct, to describe the restricted model in our slides. So B1 and B2 have the same value. Now, let's try to highlight this part for model 4, highlight this part and click run. Click run. Actually, you don't need to run this because S is the same S. Whatever you set out different models, so the S is the same. So you don't need to run this line, but you need to run SEM of the new model. Okay, now the SEM should be based on the new model M4 and S. So highlight this part. Highlight this part. This is a new M4. We just defined here. Okay, M4 here, and the same S. Highlight this part and run, and we're gonna check. Okay. Yeah, first you can try summary. You can try summary without those options. Still, the results are quite simple. It just provided you the model chi-square and the AIC, BIC. And degrees freedom, now it's 1 because we have 1 actual degrees freedom. Nothing else. Okay, so let's look at the model parameter estimate. Here we only have B1. We don't have B2 because B2 is the same as B1. So we have 5 parameters. 1, 2, 3, 4, 5. That's it. 5 parameters. Now let's look at the model fit. Try to highlight the next part. We are going to look at all of these indexes. Highlight and run. Now, the information of model fit is much more than the previous output. Okay, so first, model chi-square value. Again, this value is very important. You're gonna write it down for model comparison if you use a model chi-square difference test. Degrees freedom, probability, GFI here. Now we have the adjusted GFI, AGFI available. In the previous case, because the degrees freedom is 0, it's not convenient for us to calculate a lot of like model fit indexes. But this time we have, in addition to GFI, we have AGFI. We also have RMSEA, percentage, confidence interval, Benteler-Bonnet, NFI, which is also called the Tucker-Lewis index, and the CFI, RNI, IFI, SRMR, AIC. Okay, so we have a lot of information here. Maybe I should copy. Okay, I should copy this part to my slide so that we can do the comparison. So go to the result. Yeah, so this is the model fit part. This is for summary. If we just type in summary, that's the output. Results. Sum. But if we have the option, so if we have the option here, then we have a lot of like results. So let me try to explain the difference.
this option. So yeah, that's the information I copied from our output. So we're gonna see all of this very soon. Okay, let's try to go back to the path diagram. Now the path diagram is summarized by this. Okay, so we have B1, exactly the same number here. And the variance, covariance, variance, all numbers are ready because it's coming from the slides here. All of these are estimated. All of these 5 parameters are estimated, and we can use this path diagram to show it. In your dissertation or master thesis or journal articles, you can also show this path diagram by clearly show the numbers, and you can use the asterisk to show if it's significant or not. If the p-value is less than 0.05, you can just put a star to show. Okay, you can put a notation that means it's significant when alpha level is 0.05. So people will clearly understand the relationship among these 3 variables. Now let's go back to the result of the model fit. Let me highlight this part. Okay, this is where is it? Okay, for the first model, the chi-square value is this way. Okay, let me highlight this part. Make it purple. And then for the current model, we have the chi-square value here. And you can also use this way. Now I have a question. Okay, I have a question for you. Based on the information I provided, please use a chi-square test. Answer this question. Is a restricted model a good model or not? Restricted model is a model by putting a constraint of this. This is a good model or not? Are you going to keep this model, or are you going to discard this model? And please tell me why. Okay, why do you have that kind of conclusion? I also provide a hint. The chi-square distribution with 1 degrees of freedom. The chi-square critical value, not distribution. Okay, the chi-square critical value of 1 degrees freedom is 3.84. Okay, you're gonna compare something with that value because the degrees freedom is 1. Okay, you're gonna compare some value with that value and to conclude if it's significant or not. Come on. So yeah, tell me your idea. You want to answer that question?
I don't know about that.
You're trying.
Okay.
Yeah.
So if that's the previous slide, we had the.
Okay, yeah, previous slide. Okay, yeah, the slide, yeah, yes.
For,
This is the first model.
Mhm.
Mhm.
And then, so we're comparing the 2 model,
Which value?
the chi-square.
Exactly.
So we're comparing those 2, and then we have the critical, so and then that's compared to the critical one. So
Exactly.
we want it to be smaller than the critical. And since the second one is smaller than the 13th degree, and what was the other one?
The other one here. That's it.
So 0.05. So would the first one be a better?
Okay, so let me just, let me just repeat what he said. We have to compare the chi-square values of these 2 models. That's absolutely correct. Okay, this is the chi-square value for the second model
This is the chi-square value for the first model. The difference is really close to 0. Remember that E minus 13 is that you have to move the decimal point 3 positions ahead of the current one. So it's really small. And also for the second model, it's still very small. So almost 0 minus almost 0, it's almost 0.
Right.
So the difference score, the difference in their chi-square value is almost 0. And that value gonna be compared with the chi-square critical value with a 1 degrees freedom. Why it's 1? Because the degrees freedom is the difference, the degrees freedom is 1. And I give you the hint here. The chi-square critical value is 3.84. Then what's your conclusion? Great, you did a really good job. Yeah. Then 0 compared with this one, what's your conclusion then?
That it's a good fit. Or if it's,
Why? You missed something important between.
Because it's greater than 0.05 on the chi-square critical value table.
The values have been provided here. Yeah. Okay. Think about the. Let me show you the.
I thought that's what Hitman was referring to, the critical values. So I looked at the table.
Chi-square, yeah, chi-square distribution has a lot of shapes. For different degrees freedom, the shape will be different. Generally, it's kind of like this. Okay, generally it's kind of like this. But with 1 degrees freedom, it's kind of like this. So this is a critical value, 3.84 is a critical value. Now, the difference is almost 0. It's something here. It's almost 0. So this value is less than the critical value. Let me ask you, is significant or not? Is the difference between that model is significant or not? It's not significant. So let's translate that sentence to the full sentence. Not significant. What does that mean? What does that mean? So that means the reduced model. In other words, a model 2 with constraint is not significantly worse than the full model. They are quite similar. The difference between these two models are not significant, but the reduced model is similar because we have 5 parameters. The full model have 6 parameters. As I said, that we needed to pick a simpler model. So, shall we keep the second model? Shall we keep the restricted model or not? Yes, good. Okay. This is not significant. That means these two models are really close to each other. These two models. These two models actually, by looking at the chi-square values, these two models are really close to each other. But this model is much simpler than the previous model because here have the smaller number of parameters. Always, okay. Smaller with a model with a smaller number of models is similar than the full model. If they are quite similar, always keep the smaller model, the simpler model. So we're gonna keep this model instead of the full model. This is a really good assumption. Actually, when you check the result here, let's look at the B1 and B2. Let's check the estimate. Let's look at these two numbers. They are really close to each other. B1 and B2 are almost the same. Standard error are also quite similar. Z value probability. So our assumption B1 and the B2 are actually based on the result. It's not just nonsense. Because of the result here, we assume that B1 and B2 can be assumed to be the same. And after we run the model, we also verify that that assumption is very good because these two models are quite close to each other. It's not significant. In other words, the reduced model is not significantly worse than the full model. But the reduced model is much easier, it's much similar, it's much, has smaller number of degrees, not degrees, number of parameters. So we're gonna keep this model. This is a good assumption. Yeah, this is a good assumption. Good, thank you. That's first step. Now, let me ask you, based on the model evaluation, can you conclude this is a good model or not? Just look at, so previously we just conducted the chi-square difference test. Chi-square difference test just compare these two models. But for this model itself, is this a good model or not?
Yes.
Why?
The goodness.
Why?
Well, I was gonna say the business CLI, the
This is 0, which is really good. Nice. What else?
The goodness of fit is almost 1.
mhm.
Yeah. GFI and HIFI, both of them are almost 1, which means good. What else?
I was looking specifically at the Bentler Bunny FI as well.
Which one?
The Bentler.
This one? Yeah, this is 1, which is good. What else?
The ICUs look.
I will cover this part first, because for AIC, BIC, you're gonna compare with other models, but now we don't have anything to compare. So far, if we just focus on this part, do you have any evidence to show this is a good model?
Richard Lewis.
Yeah, this is also close to 1.
And the SRMR, you said you want it to
Yeah, this is
0.
also close to 0.
Yes.
This one is close to 0, good. This one is close to 1, good. This is close to 1, good. It's exactly 1, good. This is close to 1, good. Close to 1, good. This is 0, good. This is close to 1, this is close to 1. All of these are showing that this is a really good model. Done. Okay, congratulations, you got a really good model. But I said, but in most cases, or in reality, some index is showing really good, but some are not good. So how to choose? You can just look at all of them kind of like together. You cannot just look at one item, because one item cannot tell you if it's an absolutely good model or not. You're gonna try to look at all of this together, and then you decide. And then you're gonna decide. For example, sometimes, okay, suppose all of these are really good, but for some index, it's not good. Then you're gonna decide, okay, if I want to keep that model or if I want to make it better. And yeah, so that's it. But for the current model, all of these showing that, indicated that it's a really good model. But yeah, you mentioned that the AIC, BIC. Okay, so for these AIC, BIC, AIC, these are for comparison. If you have two models, not nested. For nested model, we're gonna use chi-square difference test. For non-nested model, we're gonna check this part. Smaller the better. Okay, but if you do the comparison between this one and the previous one, oh, I didn't copy the value. This should be very close to each other. So let's just try to look at our code, our output. This is for the model 2, the restricted model. So 10, 0.16. Let's go to the previous one. Yeah, they are very close to each other. Wait a minute. So let's try to, I'm gonna copy this part to slide. This is good. So this is from model 1.
Okay, the first part is come from the unrestricted model. The second part is from the restricted model. Based on AIC, the second one is smaller, okay? Based on AICC, the second one is smaller. Based on BIC, again, the second one is smaller. Based on CAIC, the second one is smaller. Yeah, just choose the second one. Yeah. Okay. Good. Okay. Oh, I think I repeated it. I copied it here, so it's for chi-square value. It's the restricted model. Okay, so it is a really good model. It's a really good model. Any questions so far? Any questions so far? For your homework 4, I give you a model. You're gonna write your code, whatever. Okay, if you want to use R or M plus, you're gonna run the data analysis, and you're gonna tell me if that is a really good model or bad model based on these results, based on these sets. Okay, but you're gonna tell me if it's good, why it's good. If it's bad, why it's bad. You're gonna support your conclusion by using some numbers here. Okay, any question? Okay, now let's look at independent model. Independent model. Which one is independent model? Let me just show you the pair diagram here. We mentioned this model in the first session here. That's it. This is independent model. So all of these variables are independent. So if you go to the R code, I must write the code. I must write it somewhere. So go to the code. Please find the part for the independent model. Independent model. Yeah, which line?
89.
89. Good. Yes. Let's look at this part. Let's look at this part. HE to math. Okay, let's have a review of the R code. The name of this test is NA. What does that mean? I don't want to estimate the coefficient from HE to math. It's NA. Then what's the value? It's fixed at 0. From ME to math, models education inference gonna inference math. I don't want to estimate that parameter either. I don't want to estimate the coefficient either. The value has been fixed as 0. And the covariance between HE and ME, the covariance, I don't want to estimate that parameter, the value has been fixed at 0. So this is our, but still I want to estimate the variance of ME, HE, and the variance of the residual of the MS. Okay. So that's a code for the baseline model. Highlight this part and click run. Okay, so you just run the independent model and trying to do the estimate. Okay, you're gonna run this part. So it's a model called M1. So SEM M1, the same as, and the sample size is 371. And the result is saved as M1.estimate. Okay, highlight this part and click run. Now let's try to look at the summary of the result by including all of these possible model fit indexes. Okay, run. Let's see. That's output. That's output of the independent model. Please tell me if this is a good model or not. Just look at this model fit indexes. I don't want to do the comparison of the model, this model and the current and the full model. Just look at those model fit indexes first, and then we can do the model comparison by using the chi-square difference.
No.
Why?
Well, the RMSEA is over 0.07 or 0.08.
It's too big.
Mhm.
It's too big. You're right. Yeah. What else? Yeah, that's good one. Yeah. Question. Yeah.
No, I was
Okay,
gonna say the Bentley Bonnet, the Tucker Lewis, the Bentley CFI, all those should be ones, but they're all zeros, showing that
Exactly.
it's not good.
Exactly. Exactly. What
So
else?
straight down the board.
Yeah,
The goodness of fit is far from one.
not far from one. It's close. It's
Or,
close. to one.
sorry,
Yeah. But
yes,
still,
yes. I'm tired, sorry.
yeah. You're right. All of these are 0, 0, 0, 0. Bad, 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 bad. And this is larger than 0.1. It's still not good.
Yeah.
Although this number, that's why I said sometimes if you have really bad model, but you may have really good kind of indicators, ignore them, okay? Because actually this has already told us it's a bad model. So even this value is larger than 0.9, you can just totally ignore them, okay? This one is less than 0.9. Yeah, so it's bad model. So all of this part tells us it's bad model. So independent model is bad model.
And this is basically what you're wanting us to do for homework 4.
Exactly.
This.
Yeah. If it's good, just show me why it's good. If it's bad, just tell me why it's bad. Yeah. And then we can also look at the model chi-square value. Look at this model chi-square value. User chi-square difference test. The first model without any constraint, the independent model, if you want to do the comparison by using the chi-square difference test, what's your conclusion? What's your conclusion? Why?
It has the model chi-square is large. Well, in this case,
It's large. Yeah. So the difference, the previous models of four unrestricted models of chi-square is almost 0. Now the difference is, okay, 39.67 minus 0. It's always almost this number. Degrees
And
freedom
freedom
3. So
free.
we're gonna check the degrees free. So okay, let's check the degrees free. Let me check the Q. Q chi-square. Let me check the critical value. Chi-square 3. Okay, 3 is a degrees freedom. Q chi-square. Okay, 7.815 is the critical value of 3 degrees freedom. So where's the 39? Oh, the 39 is totally larger than the critical value, 7.1. So what's your conclusion?
Nope.
Yeah, so now we have the chi-square
would
distribution.
be significant,
Exactly.
and then
So
therefore not a good fit.
exactly. So we have now the degrees freedom is 3. So have this kind of shape. It's 3.8 some 7.8 some value. And the chi-square value is it's really far with his some value, okay, almost 40. So it is significant. It's significant. Significant what? The reduced model or the independent model, the independent model is significantly worse than the unrestricted model. So we have 2 models. The reduced model is significantly worse than the full model. What should we do? Exactly. This model is really bad. Okay, discuss that. Keep the original model. Keep the original model. That's the logic. In this case, the independent model or the baseline model is nested within the full model because we put a lot of constraint on the model and we have the independent model. We have the restricted model. We can use a chi-square difference test. But if we cannot use a chi-square difference, in other cases, suppose these 2 models are not nested with each other, we're gonna use AIC to do the test, okay, to do the comparison. But again, look at these numbers. These are really large numbers. Even with, yeah, look at these numbers. These are totally, yeah, this indicated the full model, the original model is much better than the current model. Yeah, question.
So then you would always compare the independent to the full model, not the reduced model.
No, not always compare. No. This just example to show that how to compare 2 models.
Oh, I see.
But in reality, you have really two competing models, two candidates. This model should be really good. And you don't know which one should be kept. And then you run, okay, chi-square or model evaluation or SBIC to do the comparison. Yeah, yeah. In reality, we don't do the independent model because it's always a bad model. Yeah, yeah. Yeah, question? Okay.
I have a question.
Yeah.
So can we use the p-value since the p-value is smaller than?
P-value is not accurate here. Yeah.
So we cannot p-value.
P-value, look at this number, it's really, really small. Okay, yeah, let's also say that it's not a good model. But in reality, p-value is usually very small. Yeah. It's very hard to get a kind of like a p-value larger than 0.05 in reality. But still, you can get some really good models by looking at these indexes. Yeah. But in this case, it's good because it's indicated that it's significant. Yeah, it's significant.
And I have another question.
Yeah.
So like, how do we know like which one is the full model?
That's a good question. You have to make sure these models are ready and then see. Is model A can model A derived from model B, or can model B derived from model A? You have to decide which one is the full model, which one is the.
Yeah. So like for this question, like why? So how do you?
Because, okay, let's try to look at the slides here. Because this is a restricted model, we put this constraint on the full model. So this is a kind of like smaller model. This is constraint, this is constraint, this is constraint.
But how about like if we like put the single-headed error from mass to HE?
That's a good question. If you change the direction and without changes the constraint, we cannot tell because that the degrees freedom will not be changed.
Yes.
But actually the relationship is different. That's a good question. For SEM, we cannot tell the difference because the degrees freedom is the same. The number of parameters is the same. The number of information is the same.
Then like how do you know like if the full model is from like HE to mass or from mass to-
that depends on your detailed scenario. Because you have your model set up, you have to you need to have the basic logic. Why do you want to set up that model? Because in this case, I assume that HE causes math. That's why I have this cause. That's why I have this error. But if you reverse, okay, suppose if you reverse, math gonna cause math adaptation. That's not reasonable. Because
how about if we don't know the relationship, we put a double-headed error?
Yes, yes. If you don't know which one causes which one, just use a double-headed. You just say, okay, it's related, but I don't know which one causes which one.
Yeah, then how do you like decide what is the full model? Is that a single-headed error or double-headed?
Again, in that case, you will not change the degrees freedom. The direction of the direction of the arrow will not change the degrees freedom.
Yes,
yeah. So how to tell it's single-headed or double-headed? You decided. You have to decide. Okay, there is any causal effect or is any just association? But statistically, I don't.
Because like in the reduced model,
yeah,
we gonna say this model is worse compared the full model, which is like it's a like single-headed relationship or like.
No. If you just change the direction of the head, I cannot tell which one is good, which one is bad, because the model fit. You can actually, yeah.
The same. Like the degrees of freedom, like whether it's a correlation or whether it's a direct path, the statistical model, like the covariance matrix, is going to be the same.
Yes.
So you can't tell the difference.
I know that, but I just.
I mean, I get what you're talking about, like the full model. I think that's everything that you think of when to predict the dependent variable is going to be your full model. And And then whatever she's saying is derived from that full model. So instead of like the 2 independent variables, you have 3. And that becomes your full model. You're saying this is going to predict this, this is going to predict this, this is going to predict this DV. That's your full model. And then whatever you think that could be taken out from that model, like, oh, maybe just the 2 of them, that becomes that second model, that next model. So your full model is everything you think is going to happen first. Is that how I understand it? Like,
Yeah, I
it's
think
your-
that if you
it's your
change,
initial, it's your initial.
Yeah, that's how I understand too, it's like based on theory, right?
Yeah,
So you're looking at the literature in your field.
yeah,
Saying this causes this, you create that original model, and then, as you're saying, you restrict that
Yeah.
from
We
there.
test it, and if it doesn't
yeah,
count, is not significant, statistically significant, may modify the indices, or you may say, hey, this cow isn't significant, I'm gonna not test this cow, and then rerun the model to see if it becomes statistically significant. And then if it does, write yours and say, hey, I know prior theory or research shows this, my study shows that this cow isn't as significant, which does add to the larger literature.
Mhm.
What we feel.
So in the very beginning, you have to make sure each path is reasonable. You have to read your literature and
Yeah.
then you decide your model.
Yeah, my question is just like, because like just in this part of the code, I know like if you have a reason model, if you regulate the direction of the relationship and you give the reduced model, yeah, I have no question. But here, you just give the code for the reduced model,
Yeah,
but I don't see like you have regulate the original full model, the direction of the relationship.
think about that. If you just change the direction, if you still want to estimate the coefficient, the degrees freedom is no difference. There's no difference between their degrees freedom. Then for chi-square difference test, because for next model or not, you have to use a chi-square difference test. So the degrees freedom is 0. You cannot do the comparison because the degrees freedom of the original model and the full model is the same. So you cannot do the chi-square, you cannot do the test. You have to change the degrees freedom. Then you're gonna compare with the chi-square distribution, the critical value. If the degrees freedom is the same, I cannot do the test. If you just change the direction of the path. So the number of parameters is still there. Yeah, the number of information, the number of parameters is still the same. So the degrees of freedom is the same. So I cannot do the comparison. Yeah. Yeah, that's a limitation. I think that's a good question because the direction is also very important. Yeah, thank you. Thank you for that question. Any other question?
When will you release homework 4?
Okay. Good. Okay. So actually, yeah, I said you can continue the lab. Suppose that we're gonna stop here. So homework 4 is this model. Okay, the same data set, but now I assume that this is my belief. This is my model. I believe that model education gonna influence home environment, and the home environment gonna influence kids' math achievement. There's no path from here to here. I don't believe that models education gonna influence math directly. So this is my model from here to here and from here to here. And you're gonna ask me the variance of ME, variance of the HE, the variance of the math achievement. Based on this model, please do the model evaluation. Okay. So you're gonna include your code. If you use R, please provide your R. If you use M+, please provide the R M+ or ETS. If you use Immerse, then you're gonna provide your test diagram. And also provide the output, okay, the results part. And your explanation of the parameter estimate. For example, A, suppose you estimated the A is 1.2. Okay, suppose, okay, I don't know the actual number. A is 1.2, what does that mean? So you're gonna say that if models education increases by 1 unit,
that home's environment will increases 1.2 points. Okay, you're gonna explain the meaning of those parameters. And that's 2 points. And also, you're gonna evaluate your model. If the model fit the data well or not, okay, 2 points. And you're gonna state why. Okay, if it's bad, why bad? If it's good, why it's good? So 2 points. 2 points for reason, 2 points for your conclusion, 2 points for explanation, 2 points for code, input code, 2 points for outcome. Okay, 10 points. Any question? And you can choose M+, or you can choose R, you can choose EQS, you can choose MOS. Any question? Okay. Then that's homework 4. Yeah. So that's for today's class. And homework 3 is due today. If you haven't finished, then you can just, yeah, you can please submit it to me midnight tonight. Question for today's class? Okay, good. Okay, thank you. Yeah, thank you.